So this chapter is about the genomes. That's the all the DNA sequence, all right, in the all the chromosome. Okay, that's the genome. And for the genome, first of all, we will discuss the viral genome. All right. So viruses are tiny and non-living agents with very complicated lives. They are neither the prokaryote nor the eukaryote because they do not possess the structure of a cell. And the viruses are built from the nucleic acid packed in protective protein coat, which called a capsid. And some are wrapped in an additional layer of lipid and protein. So we call that envelope, all right? So we have nucleic acid, we pack into this protein coat, that's a capsid, all right? And so this is a naked virus, okay? And some, they have this, they wrap in the additional layer. We have additional layer of lipid and protein, and we call this as the envelope. So this is envelope virus, and this is a non-envelope virus. So any virus can be described as a small non-living infectious agent that is able to productively propagate in a specific host cell. Right? Each virus contains either the DNA or RNA genome coding for viral component and molecule, guiding the execution of productive viral infection. And any virus outside the host cell is completely inert, right? And they propagate only in cells that provide appropriate environment. Okay. So depend on the structural element. So the virus in nature, they fall into these two different categories. Okay, the naked virus, envelope virus. And also the viral particle is decidedly simple in superficial appearance. Okay, the nucleic acid genome is contained within the capsid, which is a symmetrical or quasi-symmetrical structure assembled from one or only a few proteins. So that's how the genome. And then the viral genome can be DNA, RNA, and then under the DNA, right, can be linear, all right, can be linear or circular. And then for the linear, you have single-strand linear DNA, double-stranded linear DNA, single-strand, that's a parvovirus, and then double-strand linear DNA, that's a herpes virus, and the M13, a single-strand circular DNA, and baculovirus, double-strand circular DNA, all right? And this is tobacco mosaic virus, single-strand linear RNA. And also we have reovirus, that double-strand linear RNA, and hepatitis D, that single-stranded circular RNA, okay? So we have these different kind of the viral genome, okay? This different kind of genome. And the virus classification, basically according to the chemical nature of the genome and the mode of propagation, right? So they are different classes. Okay, they call this as the Baltimore classification. Okay, so we have class 1. The class 1, the double-stranded DNA, that's a herpes virus. Class 2, single-strand DNA, bacteriophage M13. Class 3, double-strand RNA, reovirus. And the class 4, that's positive single-strand RNA, the poliovirus, right? And also positive single-strand RNA, also the SARS-CoV-2, also the class 4. Yes, I will also update the slide as well. I will give the new revised slide later this afternoon. Okay, and the class 4. Okay, that's the SARS-CoV-2. All right, the SARS-CoV-2 are envelope positive sense single-strand RNA virus, and the SARS-CoV-2 has 33.5 kilobase genome. Okay, and the SARS-CoV-2 genome are considered as the largest among all RNA virus. Okay, and then we have class 5, that's the antisense single-strand RNA. Now, some are envelope, some are naked, okay? It's like an influenza virus, that's negative single-strand RNA. And then we have the class 6 and 7, that's a reverse transcriptase RNA, reverse transcriptase DNA, that's HIV, that's a class 6. Hepatitis B, that's class 7. So this is the Baltimore classification, all right? And then the processes of the synthesis of viral genome are comprised of limited, all right, number of steps to ensure the generation of many copies of viral genome, capsid, and the envelope protein to be assembled into new variant. According to the chemical nature of the viral genome, the key characteristic of the replication process for all 7 classes of the virus are listed here, right? So class 1, double-strand DNA virus, right? So they replicate directly double-stranded DNA, right? And then we have class 2, the single-strand DNA, either positive, negative, okay? Then they form this double-stranded DNA intermediate and then produce either positive or negative single-stranded DNA. Okay, and then the RNA virus, so like an RNA class 4 positive single-stranded RNA, right? So they produce negative single-stranded RNA, use this as template, all right? And then synthesize a positive single-stranded RNA. They use the RNA-dependent RNA polymerase to perform this reaction, all right? So the majority of RNA viruses are replicated by the RNA-dependent RNA polymerase because they can synthesize a new RNA molecule using the pre-existing one as a template, okay? However, the double-strand RNA, this one double-strand RNA, okay, they perform their replication in a very unusual way because only copies of the sense RNA, which is positive strand, are generated. Then in parallel, the capsid protein are made and capsid assembled. Each capsid is populated with one sense RNA strand with attached polymerase. And then the RNA-dependent RNA polymerase, so RDRPS, synthesize the antisense negative strand RNA strand, completing the double-strand RNA genome. Yes, Mohammed.
So I have 2 questions. So what's the difference between the double-stranded DNA in class 7 and class 1?
Oh, this one is special because they involve some reverse transcriptase reverse transcription. So that's why they put these 2 here. These 2 are very special. They don't perform the regular replication like here. They involve the reverse transcription.
Okay, and they produce so for their virulence they end up like, what do they send to the ribosome? Is it on the bottom, on the bottom of this chart where it says single-stranded and double-stranded DNA? That's what goes in for protein synthesis?
For the virion, that's going to the virion.
Into the virion. Okay.
Right.
So that's not where the virulence is? Like I mean like the end result, like how it attacks the cell. What is the like the
This is
form?
not. These are not for attacking the cell. They are trying to package it. So basically, we are talking about here just to discuss how they replicate and package. We don't
Okay.
discuss how they lyse the cell, attack the cell. No. Yeah.
Okay. So
That'll
this is
be
not for
that'll
virulence
be
protein. Okay.
yeah. It's even more complicated. All right.
Okay.
That'll
Okay.
be even more complicated. Yeah.
But I still don't understand. So eventually, let's say if we keep talking about class 7, then it will produce a single-stranded or double-stranded DNA that will be encapsulated.
Yeah. Would be in the
Okay.
yeah.
So let me.
Yeah.
Okay. So the other ones have to go from, if they start positive, they have to go negative, and then you end up with the replicated positive RNA.
Like this one here.
Yeah, for let's say
Yeah.
number 4. Yeah.
Right. Right.
Okay.
Okay.
Thank you.
No problem. So for example, the retrovirus, the retrovirus are RNA virus, and their replication mechanism include reverse transcription. All right. So first of all, the retrovirus single-stranded RNA genome is converted into the RNA DNA hybrid, like here. They first of all convert this to the RNA DNA hybrid by the reverse transcriptase. And then the RNSH, which is the enzyme, all right, that will degrade the RNA, all right, RNSH, they degrade RNA. Then you leave the DNA. And then from that DNA, then you make the double-stranded DNA here, all right, synthesize a second-stranded DNA. So you have these, and then from here, then you generate this positive RNA. Okay, so that's the retrovirus here. Okay, that's an example. So these are the overview of mechanism of viral genome replication.
What
In
is
here, yeah.
so when you say reverse transcriptase, does that just mean that it's producing RNA from a DNA, or what does that mean?
No, the reverse transcription here, they use the RNA as template to make the DNA RNA hybrid. Here, use these as a template to make these DNA RNA reverse transcription. Reverse transcription. We will reverse transcription. So reverse transcription, that normally that means that you use the RNA as the template, especially when you for example, in the laboratory, you try to they say you try to since to genetic engineer eukaryotic gene, and the eukaryotic gene including the intron, exon. So you want to collect those messenger RNA. Those messenger RNA has been engineered so that will reflect the actual gene. So you take that RNA and then you use a reverse transcription to generate the complementary DNA, cDNA. And cDNA, then you can make it to a double-strand DNA. Do you
So
understand this
so reverse
process? Yeah.
transcriptase means you're using RNA as your template
As
and
a
you're producing DNA
yes.
and or DNA or RNA. So
So
just
in this
RNA
case,
is the template.
retrovirus here, use the RNA as a template to
Yeah.
make the RNA DNA hybrid. Yeah. In this case here.
Okay.
Okay.
Great. Thank you. Thank you.
No problem. Marina. No question. Okay, so here is just the packaging, to construct the capsid. Okay, so the process of putting together new viral particles is very complex and hardly well understood, all right, for most of the virus. Okay, some viruses spontaneously self-assemble once the viral component has been produced, and others are assisted by a specialized viral in the cellular protein. A typical example is here that I show you the helicovirus is tobacco mosaic virus, TMV. Basically, the capsid of the TMV assemble on the genome. It's driven by the protein-protein interaction between the capsomeres and the protein nucleic acid interaction between the genome, and right to package this RNA, right? That's self-assemble. And this is just an example to show the lambda and T4 bacteriophage, how they package the genome into the capsid. Okay, so that's a virus. And then the bacteria, all right? So we finished the virus and now the bacteria. So we'll do the virus, bacteria, and then eukaryotic cell. So for bacteria, right? So E. coli DNA is a circular with a length of 1500 micrometer, right? And then in order to fit this DNA, right, into a 0.5 micrometer cell, right? So they have to pack the DNA. So here you can see this nuclei. These are the chromosome, okay? So basically the DNA, basically you have a small basic protein, okay? They bind to the DNA and bend the protein. So to pack this DNA into a more compact structure so they can fit into the cell, and this is why you see the compact bacteria chromosome. We call it a nucleus. Okay, and then the protein that involved to pack these chromosomes into the bacteria cell. All right, so we need the DNA binding protein. So two different type of protein. One is a small DNA binding protein, that's a nucleic acid. Nucleic associated protein, NAP, and the other one is large protein, it's called SMC, all right? And then for this NAP, we have four different protein that involve the wrapping, bending, or bridging the DNA, all right? So the HMS, that's a histone-like nuclear structure in protein. It's a small protein. They can bridge the DNA, right? Bring the loci separated on the primary sequence level into close physical proximity. And the DNA bridging by the histone-like protein, HNS, likely enable to constrain the negative supercoil, okay? So that's the HNS. Then HU, right? And HNS, so HNS, where's HNS here, right? And then HU, all right, HU is here. It's a heat unstable, all right, heat unstable, which is another small abundant NAP protein, nucleic associated protein. They found these proteins are found in many bacteria, okay? They can coat and wrap a chromosomal DNA around itself. And the HU protein insert a conserved protein residue into the minor groove DNA to induce a sharp band in the DNA, right? To induce a sharp band of DNA like here, right? HU protein. And also the other two, IHF and FIS. IHF is an integration host factor. FIS is a factor for inversion stimulation. So IHF can dramatically alter the DNA shape and facilitate the formation of the loops, okay? So normally they can bring the RNA polymerase together with the distant regulatory protein. And IHF can also impact a range of our DNA-based process like replication, initiation, and recombination. And the FIS, basically FIS binds, these FIS, right? They bind throughout the genome. Okay, they can impact the transcription, replication, and recombination. They can also influence the chromosome compaction. Okay. The SMC, right? The SMC protein. The SMC associates to SMC protein basically they can form the extended anti-parallel coil. So they can have the hinge domain at one end and the ATPase domain at the other end, right? And then they can bring the DNA, bring the chromosome DNA together. That's SMC protein. Okay, so these are the protein that participate to package the DNA inside the bacteria cell. Okay, that's the bacteria. And then for the eukaryotic cell, okay, the eukaryotic cell, so basically, DNA replication normally occurs in the S phase of the cell cycle, all right? So we have used, as you know, we have different stage of the cell cycle. We have G1, the gap1 phase, the pre-DNA synthesis, the prepare for this DNA synthesis, DNA replication occur at this phase, all right? And then after that, you have the G2 phase, and then you enter the mitosis, okay? So you have 4 stages for mitosis. The prophase, so chromosome condense, right? Chromosome condense, and then the nucleus disappear. So from here to here, the prophase, from prophase, all right? And then mitotic spindle begin to form, and then here will be the metaphase. The metaphase, so basically spindle attached, spindle fiber attached to each chromosome, and then the chromosome align at the equatorial plane of the cell, all right? That's metaphase. Metaphase. Anaphase, so basically like here, the centromere divide to produce identical sister chromatid, right? And then they move toward opposite pole of the cell. And telomere, right? Telomere, that's a spindle disappear, and then nuclear envelope form around the 2 sets of chromosomes. So that's telomere. So that's the 4 stages of mitosis. And then as you can see from here, from the beginning to the end, because you double the DNA here, and now here you split it. So the DNA will maintain the same amount of chromosome, okay? For the meiosis, basically, you reduce the chromosome number in half because you duplicate once, but you divide it twice, all right? Divide it twice, because between the first and second division, no chromosomal replication. Therefore, you replicate once, but you divide two, you have 2 meiotic division, so that in the end, the chromosome cut in half. So mitosis maintain the number of chromosomes during cell division, so it's 2n, all right, 2n diploid. And then the meiosis reduce the number of chromosomes in half during the sexual reproduction, so the daughter cell is 1n is haploid, all right? Once you have the zygote formation, you reestablish a diploid because 1n plus 1n is 2n, the diploid number. So the haploid versus diploid number. So germ cell have a characteristic number, chromosome called a haploid number is 1n. Somatic cell, 2 homolog of each chromosome, diploid 2n. Okay. And then the chromosome, they have different centromere and the bending pattern. And normally we say karyotype. Basic karyotype, they show the chromosome arranged in pairs and sorted by size. All right. So first of all, you stand the cell, all right, and then you arrange stand the chromosome, arrange the chromosome by size from largest to the smallest. All right. So from chromosome 1 to the chromosome number 22. And when you list these arrangement, then we call this karyotype. The karyotype has many advantages, has been still used in the cytology to determine the chromosome abnormality. All right, still very popular, the karyotype, which we will discuss in chapter 13. Okay. Let me see. Okay, so maybe today we will stop here, all right? And then the next week, we will continue from this, the packaging of eukaryotic DNA into the condensed chromatin fiber. So we'll stop here today.